Today, I'll be talking about building large language models. I think a lot of you have heard about them already. ChatGPT from OpenAI, Claude from Anthropic, Gemini from Google, Llama from Meta. These are the chatbots everyone's been playing with, and they've become a cultural force. But what I want to do today is take you behind the curtain. How do these models actually work? What goes into training them, and why are they so expensive, so resource hungry, and at the same time, so powerful? Now, this is just one podcast, not a semester long course. So, obviously, I can't teach you everything, but I'll walk through the main building blocks: pre training, post training, reinforcement learning from human feedback, scaling laws, evaluation, and a bit about the systems that make this whole thing even possible. My goal is that you come away with a gut level understanding of what's really happening when you type something into a chatbot and get a paragraph back. At the most basic level, a language model is nothing more than a probability distribution over sequences of text. Sounds abstract, right? But here's a concrete example. Take the sentence, the mouse ate the cheese. A model assigns a probability to that sequence. If I scramble it into the cheese ate the mouse, the model should assign a much lower probability because semantically that doesn't really make sense. If I type the mouse ate cheese, it should again assign a low probability because grammatically that's broken. So, what you have is a statistical machine that has internalized through training what kinds of word combinations are likely and what kinds are not. And how does it do that? Through something called autoregressive modeling. That just means you take a sequence of tokens, tokens being not quite words, not quite characters, but somewhere in between. You train the model to predict the next token, given everything it's seen so far. You do this over and over, billions or trillions of times, until the model is really good at continuing text. That's why, when you ask it a question, it doesn't really think. It just continues from your prompt in the way that's statistically most likely. Now, an important aside here is tokenization. People often forget how critical this is. You can't just feed raw words into a neural network. You have to break them into smaller pieces, subwords, or even bytes, so the model can handle typos, strange character sets, or languages that don't have spaces, like Thai. The most common approach is called byte pair encoding. Imagine starting with every single character as its own token. Then you look at pairs of characters that appear frequently, like T or ER, and you merge them into new tokens. Do this repeatedly, and you end up with a vocabulary where common sequences have their own ID. That's why in English, something like tokenizer might split into token plus izer, while in code, the four spaces at the start of a Python block might even become their own token. Tokenization sounds like a boring pre-processing detail, but it really matters. Bad tokenization can cripple a model's ability to understand numbers, math, or programming languages. Once we've defined tokens, the model learns to predict the next one. During training, it outputs a giant probability distribution over the entire vocabulary. If your vocabulary has 50,000 tokens, the final layer of the network is a vector of 50,000 numbers. You compare that distribution to the actual next token, which is represented as a one hot vector, and you compute the cross entropy loss. That's the mathematical way of saying make the probability of the correct next word higher and the probability of the wrong ones lower. Do this enough times and the model internalizes patterns. Now, how do we evaluate whether the model is any good? One metric is perplexity. It tells you, on average, how many tokens the model is hesitating between at each step. Early models hesitated between 70 possibilities for each word. State of the art ones today hesitate between fewer than 10. That's progress. But perplexity has limits, especially once you start to doing post training. At that stage, the model is no longer just a statistical parrot of internet text. It's being nudged into behaving like an assistant. So perplexity doesn't capture the full picture. And that brings us to data. It's not literally every web page. In practice, researchers start with something like Common Crawl, a massive, messy scrape of billions of pages. Then they filter aggressively, strip out HTML, remove boilerplate like headers and footers, filter out toxic or private content, deduplicate, balance across domains. They downweight entertainment gossip, upweight code and academic text, and at the very end, they usually polish the model with a pass over high quality sources like Wikipedia. Even then, it's messy. The open source benchmark called the PILE shows this distribution. You've got Archive papers, GitHub code, PubMed articles, Stack Exchange Q&As. That's the raw fuel of intelligence. And here's a number to put it in perspective. Today's strongest models train on around 15 trillion tokens. That's two orders of magnitude more than the early GPT-2 days. So, if pre training is about raw knowledge, learning to mimic the internet, post training is about shaping behavior. Pre training gives you something like GPT 3, powerful but often weird, sometimes incoherent, sometimes offensive. Post training is what turns that raw model into ChatGPT, an assistant that follows instructions, refuses harmful requests, and explains things at the right level of detail. The simplest form of post training is supervised fine tuning or SFT. You collect a dataset of prompts and good answers, and you fine tune the model to imitate those answers. It works, but it has big limitations. One, you're bound by human ability. If I ask you to write a book, you can judge which book is better, but you probably can't write the book you'd ideally want to read. So, cloning human responses locks the model to human mediocrity. Two, SFT may actually encourage hallucination. Think about it. The model has seen trillions of words, but maybe it never saw this particular book reference you put in your SFT dataset. To it, that reference looks like a plausible string of words. When you fine tune it to reproduce that, it learns to fabricate similar plausible sounding references, even if they don't exist. That's one hypothesis for why hallucinations persist. And three, cost. Paying humans to write thousands of high quality answers is really expensive. That's why reinforcement learning from human feedback came in. RLHF flips the script. Instead of cloning answers, you ask the model to generate two responses, and you ask a human which one is better. Humans are much better at choosing between options than they are at writing from scratch. Once you've collected thousands of these preferences, you train a reward model that predicts which answer a human would prefer. Then you fine tune your main model to maximize this reward. Originally, OpenAI used reinforcement learning with PPO for this. It was messy, complicated. Reinforcement learning is always messy, but it worked. That's what made GPT 3.5 and ChatGPT cross the chasm into mass adoption. Over time, researchers realized there's a simpler way: direct preference optimization, or DPO. Instead of building a reward model and running full reinforcement learning, you can just maximize the likelihood of preferred answers and minimize the likelihood of dispreferred ones. Mathematically, under certain assumptions, it's equivalent to PPO. Practically, it's way easier. That's why today most open source models use DPO or something similar. Now, there are subtleties here because human annotators, when shown two answers, often pick the longer one. And once that bias creeps in, the model optimizes for it. That's why sometimes ChatGPT writes paragraphs when you just wanted one sentence. Evaluators now try to control for this, but it shows you how even small biases in training data propagate. Another subtlety is who the humans are. If your annotators are mechanical Turk workers in one country, you may get very different judgments than annotators in another. Whose preferences are you encoding into the AI? That's a live ethical question. And speaking of evaluation, how do we actually rank these models once they're aligned? You can't just look at perplexity anymore. Instead, you run head to head comparisons. There's even a platform called Chatbot Arena, where people chat with two anonymous models side by side and pick which answer is better. Collect enough votes, and you can build a ranking. Interestingly, researchers have also started using large language models themselves as judges. You feed two answers into GPT-4, ask which is better, and average over thousands of examples. Surprisingly, this correlates with human rankings about 98% of the time. It's fast and cheap, though it also inherits the biases of the judge model. Let's zoom out for a second. All of this training, pre-training on trillions of tokens, fine-tuning with SFT, optimizing with RLHF takes an insane amount of compute. Models like Llama 3 with 400 billion parameters are trained on tens of thousands of NVIDIA H100 GPUs running for months. We are talking 50 to $100 million per training run, plus massive engineering teams. That's why there are only a handful of labs in the world that can do this at frontier scale. And that's why scaling laws matter so much. Scaling laws are one of the most surprising findings in AI in the last decade. They show that if you increase model size, data size, and compute, performance improves in a predictable way. Plot loss versus compute on a log-log scale, and you get a straight line. That means you can extrapolate. If I give you 10 times more GPUs, you can tell me almost exactly how much better your model will be. That's astonishing. It's also why companies are comfortable spending tens of millions. They know ahead of time it won't be wasted. There's even a sweet spot known as the chinchilla ratio. Roughly 20 tokens of training data per parameter for optimal efficiency. Train too big a model with too little data and it underperforms. Train too much data on too small a model and it also underperforms. Get the ratio right and you're in business. Interestingly, when you account for inference cost, the cost of running the model after it's trained, the sweet spot shifts toward smaller models. That's why companies like OpenAI and Anthropic now talk about model families. A huge flagship model plus smaller distilled versions optimized for deployment. Systems optimization is the unsung hero here. People focus on model architectures, but the truth is, transformer architecture hasn't changed much since 2017. The big breakthroughs have been in data, optimization, and systems. For example, using lower precision arithmetic, switching from 32-bit floats to 16-bit or even 8-bit, cuts memory in half and doubles throughput, with almost no loss in accuracy. or operator fusion. Instead of sending data back and forth between GPU memory and compute cores after every PyTorch operation, you fuse multiple operations into one kernel. Suddenly, your training loop runs twice as fast. These tricks, multiplied across thousands of GPUs, save millions of dollars. Now, let's come back to alignment for a moment. One critique of SFT is that it's basically behavioral cloning. You're asking the model to imitate what humans wrote, but you're not necessarily encouraging it to surpass human ability. RLHF solves some of that by optimizing for human preference rather than imitation. But even RLHF has issues. Reward models aren't perfect, they can be gamed. That's why researchers are experimenting with approaches like constitutional AI, where you hard code principles, or AI feedback, where stronger models help judge weaker ones. The field is moving fast, but the core insight remains. Raw pre training gives you knowledge, alignment gives you usability. So, where does this leave us? Training large language models is a blend of brute force and elegance. Brute force in the sense of trillions of tokens, millions of GPU hours, and billions of dollars. Elegance in the sense of clever algorithms like DPO, scaling laws that let you predict the future, and systems, tricks that squeeze every last drop of efficiency from hardware. And perhaps the most important takeaway is this: the breakthroughs that mattered most weren't exotic new architectures. They were about doing the simple things at scale with care. Train on more data, balance that data carefully, use scaling laws to allocate resources, align the model with human feedback, optimize your GPU pipelines. That's it. That's what turned academic curiosities into the tools billions of people now use daily. When you open ChatGPT or Cloud or Gemini, you're not just talking to a chatbot. You're interacting with the product of decades of research in probability, optimization, systems engineering, and human computer interaction. And the next wave, whether it's multimodal models that see and hear or agentic systems that act in the world, will build on exactly these foundations. So the next time you ask an AI to explain photosynthesis to your kid, or to debug your Python code, or to draft a business email, remember, under the hood, it's still just predicting the next token. But wrapped around that simple mechanic is an extraordinary scaffold of data, algorithms, feedback loops, and engineering ingenuity. That's the real magic of large language models.